Yes.
So let's continue with the language models discussion. So previously, so let's have a recap of things which we have discussed previously. Uh, so the language model is like some system from which you can get the probability of a sequence of words, or if you give the sentence, it gives some probability value that saying that this particular sentence is um, what is belongs to the sentences of the language, or a valid sentence in that language. Or the language model can be uh, po- uh, the problem can be posed as a next word prediction problem, like you are given some words till t minus 1 and you predict the next word, and what's the probability of that conditional, I mean what's that conditional probability. So it's like the, say here you can see the students often there can be n number of possibilities, like it can be a book, it can be laptops, exams, or minds, and the language model will give a distribution saying books has uh, uh, this much probability, like I said, that will be a number between 0 and 1, and our laptop has this much probability, and for the entire words in the vocabulary there will be some value associated with it, and all the value will add up to 1. And to calculate for this particular conditional probability, you can find the probability of that n grams and divide by the n minus 1 gram. And these probability can be estimated by counting the number of these n grams, or n minus 1 grams in the corpus, in a large corpus, and you estimate these counts, and then during your calculation you use these counts to create the probability values. So the same thing, like you have a sequence of words and you are predicting the next word. And this thing which we have missed, and we directly jumped into the RNN, like same as the n-grams, you can also have uh, neural language models with fixed window. Like here you can see a window of four four words: x1, x2, x3, and x4. Am I audible?
Yes, yes.
And you some way you convert these to some vector, like using one port representation or some other vector transformation process, and you concatenate and feed it to a regular feed forward neural network, like the you multiply this whole vector with a weight matrix and add a bias and pass it through uh, um, some nonlinear function, and at the end you convert that resultant vector to a probability distribution using softmax. So you can train this neural network uh, through back propagation, and at the end you have the model, which is your uh, weight vectors as well as the bias vectors, and you don't have to store the entire count of to store this um, and in the RNN we have seen that RNN is like a what do you call, like a mixer or a juicer in which you add different ingredients, and it keeps on uh, churning the things, and you get an output at every step. And in the sequence of any lung can be fed into this RNN, and it's kind of a recursive process, like there will be a hidden state which will be updated at every time step, and input will be going in uh, at each time step, like the words will be going in each of these time steps, and the hidden state will be updated, and in during the training, the weights. So one thing here is like, even if there is an very large sequence, the weight matrix used is the same for every stage, and during each during the training, at each step, these weight matrices are adjusted uh, by propagating the error functions. So it's like, how do you update these weights? Is like you calculate, you have an error function, or the, I mean, the cumulative error, and you wanted to update the weights with respect to your this particular hidden state, like this particular step, and this particular step some error has occurred, and I wanted to update that weight, but you had this 4 time steps, and at the at the end of the step 4 you want to update the weight for adjusting the error that might have happened at the first stage. So it's like you calculate the uh, gradient with respect to gradient of the error with respect to the that hidden state. It's like in gradient descent, it's like gradient descent is process like you explore the gradient of the error in such a way that your aim is to reach the value of that error, like the minimizing the error, and you have the notion of like which direction you have to follow to reach that value quickly. Like it's the direction of negative of the gradient, or the opposite direction of your gradient. Like if it's a negative slope at one point, it's a negative slope means like the if you increase your the parameter, like this hidden state h1, then you are going towards the valley. Or if your slope is positive at that particular point, and if you increase h1, you are reaching a point where the error is more than the current stage. So you know like which direction you have to follow, and to practically do the calculations, you can apply the chain rule and see like it's like the whole gradient is like uh, uh, multiplication of different gradients of each of the states, and you see like there are four different things getting multiplied together. And with these thing, like the sequence can be of any length, like in a sentence, like uh, a sentence can be of any length, like you can always create bigger and bigger sentences in any of the languages. And so what happens if one of these gradients are small, like the whole product is going to be very low, and you won't make much changes in weight with for one of the, I mean, the earlier sequence stages. Like that's the problem here in the vanishing gradient. When one of these gradients are smaller, like the whole product gets smaller, and the updates to the weights are going to be small, and it's like you don't learn anything for long sequences, or this long-term dependencies are not captured in the system. So any questions so far?
No, like I was gonna ask like the solution for this and like, the vanishing gradient.
So the same thing, like the for long sentences, like if there is some dependency uh, for the next word prediction coming from the start of the sentence or start of any other sentence which are long back in the sequence, are not captured in this system. due to this, most of the time due to this vanishing gradient problem. So it's like if the dependencies is not captured, means if the gradient is, if you consider just the gradient, like the gradient is becoming very small over the long distance, it means like two things. Like one is like there is no dependency at all. Second thing is like it's the model is not able to capture the dependency. So if it's in vanishing gradient problem, the thing is like the model is not able to capture this long-term dependency. Like the say here you have a you want to predict a next word. Like there is this big group of sentences. Like when she tried to print her tickets, she found that the printer was out of toner, and she went to the stationery store to buy more toner, and it was very overpriced. After installing the toner into the printer, she finally printed her what? Uh, can you
Tickets,
predict
I
tickets?
think.
So the tickets are coming from the idea of tickets is coming from the first sentence. Like it's a long-term dependency. Like if you ignore this part and see all the other sentences, you won't be able to predict this part. So it's like the that's the problem with the vanishing gradient. Like in application, how it comes out. Like and now we have to see like how to deal with this problem. And also like the so in another words, like another, if you look at another issue, like the consider this sentence, like the writer of the books, it could be is or are, but the correct thing is is, because it's dependent on this writer, not on the books. But due to the vanishing gradient problem, the model may predict like uh, R is the R with the more probability. So that's the one of the this, I mean, same problem, but like the syntactic recency, I mean the sequential recency get more predominance over the syntactic recency in these RNN models. And the same way, there is another thing, like if the one of the gradients is too big, then the problem, there is a problem with a problem called exploding gradient. Means like that overall product becomes very large, and it won't be, the system won't be able to keep that number in its bit limit. Like if you are using a 32-bit unsigned integer, then it may go beyond that, and then the system will represent it as not a number or high enough, and then you have to go back and see what happened. Something clipping is one of the exploding gradient can be quickly solved by gradient clipping. Like if the gradient is going beyond a threshold, limit that within the threshold, but keep the direction. Like you divide it by the uh, what do you call a norm of that vector, and keep the same direction. And how to fix the vanishing gradient problem? In so we have seen that in vanishing gradient, like the RNN is not learning long-term dependencies, and in the normal vanilla RNN, you can see like the hidden state is getting updated at every step, and there is no control over how much it needs to be updated, and can I stop the updation for one step, or can I have the updation only for certain steps. So there is no control over hidden state updation, like it's automatically getting updated with this recursive formula. Like you multiply the previous hidden state with some weights, and then add it to the weighted inputs plus some bias, and pass it through a nonlinear function and update the hidden state. This is automatically happening. So one way to solve the vanishing gradient problem is, like, people thought about like having a memory, like memory which can be activated and deactivated. Like you have So from that came the idea of LSTM, long short-term memories. So you have in this is like it has a built-in memory cell, and it can store two states. One is a hidden state, and the other is the cell state, HT and CT. And these both of these are vectors of a fixed length, and uh, there are gates with which LSTM can erase, write, and read information in these both of these states. And the gates are also vectors of length n. Like it's like for each of the say cell state you have n elements, and the gate will also have n elements, and the gate is like the gate is going to be multiplied with this state, and if the element is 0, it's like that element, that particular element of the gate is 0. That means that that particular element, the corresponding element in the that state vector is not going to be passed, or it's going to be, it's like the gate is closed for that particular element, and the value can be between 0 and 1, and so that you can pass only certain what do you like what do you call like this weight. It's like the weighting each of the giving weight to each of these elements in the cell state, or uh, for the input or the hidden state. So these different gates can uh, act as a door. Like if it's 1, it's completely the information is completely passed. If it's 0, it's like completely closed, and in between, like it's partially passed. And these gates are like uh, neural networks on its own, and it can be these the weights and biases of this can be trained through back propagation. And this is the holistic complete picture of an LSTM cell. So mainly, like if it may look like very complex thing, but it's very simple. Like if you look like is the input gate, and the third one is the output gate. And you have two states, like the CT is the cell state, HT is the hidden state. And all these gates are a kind of neural network. Like it has bias weight vectors as well as the biases. And what does this forget gate do is like so you have this this is your forget gate. Like you have the previous cell state, and it determines how much of this previous cell state needs to be passed forward to the next cell state. And the input gate, you can see the input gate here, which controls this the how much input needs to be passed to the cell state. Like this thing is the concatenation, like the hidden state, previous hidden state, and the input is and passed needs to be passed to the cell state. And there is an output state, output gate here, which uh, determines how much of this cell state needs to be passed to the uh, hidden state. And ठीक है. And let's see like how much this LSTMs got impacted the NLP domain. Like in 2013 and 15, the LSTM were the state of the art methods, and so it's been successfully included in handwriting recognition, speech recognition, machine translation, parsing, image captioning, and all those things. But I mean, this today, like transformers have come up, and those being the dominant approaches in the current situation. Like there are different transformer architectures which being widely used and giving good accuracy and good performance. We'll talk about transformer after this RNN stuff is finished. And we have looked at the LSTM, like it has the three different gates, and someone came up with a simpler model with only two gates. One is the update gate and the reset gate. So you can see the comparison of these three different RNNs, like the vanilla RNN, LSTM, and GRU here. And what has changed in GRUs, like there is one gate which is doing two functions. Like there is this update gate. Update gate is used here. You can see like the 1 minus update gate and update gate like value into HT. So it's being used at two places, and only one state is there, like the only the hidden state is there. There is no separate cell state. And so reset gate is somewhat like the forget gate. So it's the same way it's operating here, and in the update gate, does like how much the current HT needs to be, the calculated HT needs to be there in the actual hidden state, as well as how much the previous hidden state needs to be passed to this HT. So both being done in one with the one gate. And in comparison, like it's only not much bigger difference between the GRU and the LSTM, but only thing is like GRU fewer, and the weights and biases are also, I mean, only for the two gates. Then the parameters are fewer than LSTM, and performance wise, no conclusive evidence like the one performs better than the other. Like the better way is like you can start with LSTM, and if it works, and you can change it to GRU and see it's working again, and then go with GRU. And there are other solutions to vanishing gradient problems also, like in the uh, neural network architecture itself, like there are things called ResNets. So it's not very specific to the vanishing gradient problems are not very specific to the RNNs alone. Like it's there in any neural network which has multiple layers, or which are kind of a deep networks. So in CNN and all, you have seen like ResNet, this residual connections. Residual connections are the identity function, or the previous inputs directly being fed to the that particular layer, instead of all being coming through the different previous layers. So it's been seen like the with these connections, the some dependency, long-term dependencies can be like the uh, layers. There is always one more input coming directly to this particular layer. And the dense net also has similar idea, like in this every layer is connected to every other upcoming layers, like it's the dense connection. And there is another idea like the highway net, where it's like ResNet, but with a dynamic gate, like it can determine like whether this information needs to be passed, or uh, don't needs to be uh, doesn't need to be passed. Like there'll be some trainable gate just like LSTMs, and so it's a combination of this LSTM idea and the RustNet idea. So that's about vanishing gradient problem and its solutions. And in our next lecture, we'll have discussions on bidirectional RNN and multilayer RNN, and we can also start with transformers. Any queries?
The GRU architecture,
Huh.
just is it like just because like there are less number of gates? I mean, like it's quicker and all.
One thing is like you are during the training, you only need to update fewer parameters, and also during your inference, you only need to do uh, lesser computations.
Mhm.
And
Okay.
it's been seen like in practical situations, the LSTM and the GRU are not differing much in their performance, even if LSTM has these three different gates.
Mhm. And like, how does it know like what to forget and what to keep in the memory? The like LSTM for LSTM's case.
So each of these gates are neural networks on its own. Like it gives a probability distribution with the n number of what do you call n number. Uh, uh, it's it outputs an n number vector with all the entire thing as a probability distribution, and you are learning these gates like these weights and biases are learned through experience, like these sequences are fed and your problem is predicting the next word. And if the during the training, if the in first go it's predicting wrongly, the error is big, then you propagate that error and update these gate weights and biases. So uh, with a very large corpus and you are training it on for a longer time, your weights and biases will get adjusted in such a way that it uh, always gives a good accuracy. Like for example, in that previous tickets case, it would know like the what should be the gate value. Like when it the first when the first tickets while example comes, like it updates the uh, cell state or the hidden state in such a way that the I mean gates are give more importance to these that first tickets, so that it's captured in the system. So the gates needs to be gates will converge or train in that way with a good number of training examples.
Mm-hmm. Okay.
It's like you where you want which information is more important for you. That is captured with that gates.
Okay. And that is decided based on like the training corpus and all.
Yeah, it's automatically learned. It's like
Mm-hmm.
you are creating a system which for us humans, like we can detect some rules and things, but in the machine learning thing you need to the system needs to learn or generalize on training example and have these rules set up automatically. Like we cannot go and tell like this is the rule. That's not the way the this machine learning work. Like it's solely depend on data examples. So you give enough data examples and the system learns or generalizes on those examples.
Mm-hmm. Okay.
Anything else?
No, that's it from my side.
Nothing from my side.
Yeah, and so the next lectures we will see the multi-layer RNNs and bidirectional RNNs. So you have noticed like in this RNNs the sequences are loaded from in one direction. Like say if it's the sentence is like how are you, like that's being fed like how first, are first, and you first, you then. So it will be
Mm-hmm.
in that sequence, and you only look in one direction for next word prediction. So in bidirectional it's like it's able to look in both direction. And
It goes back as well.
yeah, multi-layer is like the same way as the multi-layer perceptrons or other neural networks. You can add multiple layers to this RNNs also. Like, and we'll see like what are the practical use cases and how, like how do you train an RNN model and all those things in the next lecture.
Mm-hmm. Okay.
Okay.
ठीक है then. Thank you so much for your time. Have a great day. Bye bye.
Thank
Okay.
you.
Thank you.
Bye.
Bye-bye.